Hey folks, all right, so the first one we're going to do is from the 2012 AP exam, free response question number 1. As I said before, I do strongly recommend that you try these problems on your own before either checking the solution or watching this video. It can be very easy to think you understand it when you're looking at the right solution, but generating that solution on your own is a different task entirely. Okay, so let's get started. This problem we're given what's something that looks like an Atwood machine, but at first we just have one mass A, sliding on a horizontal surface. It tells us it does have friction, it gives us that coefficient, and it tells us how much force is acting on the end of the string. First part is just to draw and label each of the forces acting on mass A free body diagram, basically. Okay. So the forces acting on mass A, of course we have gravity, mg, we have normal force, and those two should be the same length or as close as you can reasonably get by hand. In the x direction we have tension to the right and friction to the left, and since we know the problem tells us the block is going to end up accelerating to the right, we should make sure that the tension arrow is longer than the friction arrow. It indicates the relative magnitude of those forces. Okay? And that's it for part A. That's it. That's the whole thing. Part B, magnitude of the acceleration of the block. Well, this is just a straight up Newton's second law problem, F net times A. And since A is going to be purely in the x direction, and I'll say to the right is positive, and I only have to do forces in the x direction. Okay. Now it can be helpful here. You could probably jump right to this, but it can be helpful looking at the y direction and saying that the net force equals 0 gives you that the normal force is equal in magnitude to mg. Now, why is that going to be helpful? Well, because we're going to be dealing with friction in the x direction, and remember, friction is mu times the normal force. The x m times a. The net force, of course, is, if I say to the right was positive, then the net force is tension minus friction equals m times a. Okay, coming up here to continue, I can solve this for a, and at the same time plug in for friction mu times normal force divided by mass. One last development on the friction, that the normal force is m times g divided by m, and now I can plug in the values that I'm given. 15 minus 0.25 times 9.8, I'm doing this a little out of order, but that's okay, 2.0, not 2.8, okay, divided by the mass of 2.0, and you'll find that the acceleration is about 5.1 meters per second squared. Okay, so they really do want to see that F net equals ma. In the solution, they don't address needing to see the y direction, but you definitely want to write out all the steps in the x direction. Okay, moving on. For part C, the problem is changed a little bit. That applied force 15 newtons is removed and replaced with a block at the other end of 1.5 kilograms. They want you to sort of resolve the problem. Now, the trap they are setting for you is, you may see this and think, oh, well, the force pulling on the other end of the string is now the gravity on B. Well, that's about 15 newtons, right? 1.5 times approximately 10. So shouldn't that mean that the system has the exact same acceleration? It's the same thing, isn't it? It's not. Okay, it's not. Because, for one, you've added mass to the system. The mass of the system is no longer just the 2 kilograms, it's 1.5. But also this gravitational force does not directly translate to what the tension is. Okay, because B is moving, okay, the tension is not perfectly canceling out the gravity on B. Okay, so don't fall into that trap of like, oh, it must be the same. Take your time and solve it like an Atwood machine, right? Sort of ignore the fact that we did the first part of the problem because this is an entirely different system. Okay, so the AP acknowledges that there are two ways to solve this problem. One would be to draw a free body diagram for each mass individually and then sort of combine the equations you get, or you can solve it as a system. And we've done that more often, so that's the method I'm going to show. First thing I'll do is choose that as the positive direction. And when you're solving it as a system, they really want to see some indication of the fact that you're combining them into one overall mass. So mass total equals mass A plus mass B. And they, you should also show that they net force is mass total times the acceleration. Okay, so the net force here, one of the total forces, remember, net external forces acting on the system. Gravity, mBg, and the friction back here holding it back. Why not include the tension? Well, remember, when we're considering this a system, the tension is an internal force. The string is moving with the blocks. Okay? The string is moving with the blocks. So my net force, okay, ends up looking like, if my positive direction is as I chose it, mass B times G minus the friction, which we already showed, is mu times mass A times G equals mass total times the acceleration. Okay, all I have left to do is solve this for acceleration, which is pretty straightforward. You could plug in numbers anytime here, and also plug in this is, of course, that's mass total. And when you plug in all your numbers here, you find that indeed it is a very different acceleration from part B. You get about 2.8 meters per second squared. Okay, so don't fall into the trap they're setting for you here. It is a different system when you have a block versus a specified force on the other end. Okay, moving along, part D, calculate the tension in the string connecting the two blocks. Well, the tension, the way we solved it in part C, the tension was an internal force, so it didn't appear. What we need to do is focus on one of the two masses in order to find the tension there. Now, mass A has, again, 4 forces acting on it. Mass B has only 2, so that's the one I'm going to choose, is mass B. Mass B has, of course, the tension acting up and gravity acting down. Just go ahead and... But here, again, we're using it just for mass B. Okay, so you can choose whatever direction you want to be positive. So before I had sort of down is positive here, so I'll keep that. And I'll say that then mass B times G equals mass B times the acceleration. Plugging in my known values and solving for tension, I get tension equals mass B, which is 1.5, times 9.8 minus mass B times the acceleration, which is 2.8. Now remember, that's down, but down is in my positive direction. Okay, so tension. All right, let's pull up my little calculator here. I have 1.5 times 9.8 minus 1.5 times 2.8, and I get a tension of 10.5 newtons. Okay, so again, just a different application of Newton's second law. Okay, part E, hopefully this is pretty straightforward for you guys. Here, calculate the distance that that block B, the 1.5 kilogram block, descends in 0.4 seconds. Okay. One important point, it does say distance, so I'm not worried about positive or negative direction. It's just a distance. It's a number of meters. And this is a kinematic problem, right? I know the initial velocity, it tells me in the problem that everything starts from rest. I know the acceleration is 2.8 meters per second squared. This part gives me the time of 0.4 seconds. So this is a straight up kinematic problem. So we can say why this is probably the best equation to use here. Okay, just indicating that all of these values are to be in the y direction. My initial position, I'll call that 0, so that goes away. Initial velocity was 0, that goes away. So the distance I move is 1/2 times 2.8 times 0.4 squared. And I'll pull up my calculator again. 1/2, so 0.5 times 2.8 times 0.4 times 0.4 equals. And I get a distance of 0.224 meters. Okay, so that's all the calculation for this problem. Major points are remembering how to solve an Atwood machine as a system, making sure that you indicate that you are doing that. Okay, if you just jump right to something like this, you may miss out on a point. And at that point, of course, is assigned for indicating that you're solving it as a system. Other important point, as I said a couple of times, this problem is not the same as the beginning. You may be tempted to think so, and they want you to fall into that trap. That's the one they're setting, but don't do it. There was one other part, part D, or excuse me, part F, I guess, to this problem, which says if you set up this system, okay, this one here, in a lab, right, and had all of the calculations correct, all of your predictions made, and you experimentally find that the real acceleration is something less, maybe 2.6 meters per second squared. It doesn't give you a number, but it says, what if it's less? Okay. Now, assuming that your number for friction is correct, what's going on here? Why is it less? So I want you to do sort of an explanation of why that is. Okay. This is not a particularly easy thing to see, but remember, there is a pulley here. Okay, and as the system accelerates, the pulley is rotating. Okay, so even the best pulley, even if there was, by the way, there'd be friction at that little axle there, that rotation point, so we've got a little bit of friction there, but even if there wasn't, it eats up some energy to rotate that pulley. We learned that in our torque and angular unit. Okay, so that's where some of that energy goes. It goes into rotating the pulley, whether there's friction there or if it's just the rotational kinetic energy of the wheel itself. That's going to eat up a bit of the energy of the system. So that's why it would experimentally be slower than what you predict.